Good day, students. In this clip, we're going to be going over differential equations. I took a look at the 2006 to 2013 free response questions, and I consolidated them in the context of one problem. And we're going to be reviewing the different questions that can be asked for differential equations, all right? So we're going to be going over how to find particular solutions of a differential equation with an initial condition, how to generate slope fields, how to write down the equation of the tangent line or find the linearization of a function at a point, and how to use that to estimate, and also the concavity. Okay. If I do not finish all the problems in this first clip, do subscribe so you can get updates to the subsequent clips. Alright, so now let's take a look at the question. So it says, consider the differential equation dy dx equals y plus 1 over x squared, where x is not equal to 0. Let y equals f of x with f of 1 equals 2. Part A. On the axis provided, sketch a slope field. So we're going to sketch our slope field here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 points. We're going to draw the tangent line for 9 points. Tangent line to the equation that has this differential equation right here. You notice that this x-axis, the y-axis has no points on them. Well, that makes sense because we know that x cannot be 0. If x were 0, in this differential equation, we're going to have an undefined slope. So that's why these points along the y-axis were excluded from our graphing points, okay? So what we're going to do is basically make a table of values here and go ahead and graph our tangent lines. So let's make our table of value. So I'm going to have my x, my y, and then the computation of my slopes. So the way I like to do it, I like to do it in order. Alright, so I have my two table of values. So I'm going to use the x and the y coordinates to find out what the value of y plus 1 over x squared is, which is basically dy dx, as indicated in the problem above. Alright, dy dx is y plus 1 over x squared. Alright, so let me set up my table of values right here. So y plus 1 over x squared is equal to dy dx. Okay, so I like to do it in rows. So we're going to do columns. I'm going to do the first column first, where x is negative 2. So for that one, we have negative 2, negative 2, negative 2. And then when x is negative 2 here, what is the value of y? It goes from 2 to 1 to 0. Okay? And then for the next column, we have negative 1, negative 1, negative 1. And then y exhibits the same behavior. It goes from 2 to 1 to 0. And then for the last column, x is constantly 1, so we have 1, 1, 1, and y does the same pattern, 2, 1, 0. Alright, now let's go ahead and compute our slopes. The first one we have is just add 1 to the y-axis, so that's 2 plus 1 divided by the denominator squared. Negative 2 squared is 4. So dy dx in this point is 3 over 4. So that's what the slope of the tangent line is going to look like. Alright, next one. Y plus 1 is 1 plus 1 over the denominator squared, which is 4. 1 plus 1 is 2. 2 over 4 is 1/2. And then the next point, we have 0 plus 1 divided by negative 2 squared again, which is 4. And that gives us 1 over 4. So those are the slope of our tangent lines for the first column of points, where x is negative 2. Now let's advance to the column of points where x is negative 1. So we have y plus 1, 2 plus 1, divided by the denominator is negative 1. When you square that is 1. So 2 plus 1 over 1 is 3 over 1, which is 3. Find the next point, y, which is 1 plus 1, over the denominator squared, which is 1. 1 plus 1 is 2. 2 over 1 is 2. The last one is going to be 0 plus 1 over the denominator squared, which is 1. 1 over 1 is 1. Alright? Now let's take a look at this one right here. You're going to find out that this output will be exactly the same as this because we're squaring the denominator, which means that the denominator is going to be positive regardless of the sign. Alright, so let's go ahead and work it out. Y plus 1, 2 plus 1, divided by the denominator squared, which is 1. Output is 3. That's the slope. Next one is 1 plus 1, divided by the denominator squared, which is 1. So we have 2 over 1, which is 2. And then lastly, 0 plus 1, divided by the denominator squared, which is 1 squared, is 1. Alright, so we have all our slopes for the tangent lines. So let's go ahead and graph it. I like to do it column by column, so let's do the -2 columns first. So for the -2 column, it's 3 over 4. So you can think about it, you're going to graph it rise over run. So you're going to rise 3, 1, 2, 3, and run 4. Okay? So it's kind of hard to fit it in here. So one thing you can do is, instead of going to rise over run, you can fall and go back. It's the same thing. Okay? So let's fall 1, 1, 2, puts another point 3, and then go back 1, 2, 3, 4. Okay, so this is just an estimate. So think about a line. So what you want, if you want to graph this tangent line, you're just going to put a ruler on these 2 points and just draw a snapshot. Okay, so let me draw the entire line right here. So that's what the line is going to look like. It's a little bit off. Let me fix that. So bring it down. So the line is going to look like that. But so all I don't need the entire tangent line. I just need a snapshot. Okay. So you see that line, you place your ruler there, and then when you draw your tangent line, it's just a little segment or a snapshot. Okay. So that goes 3 over 4. All right. And then let's shift to this one. It's 1 over 2. So you rise 1 and run 2. 1, 2. Okay. Rise 1, run 2. So we're looking at a line that goes through these 2 points right here. We just need a snapshot of that tangent line. So let's see, a line that goes through those 2 points. But I just need a snapshot. So you just draw a small tangent line there. Okay. All right. And then the next one is 1. So you rise 1 and run 1. So we need a line that goes through these 2 points. The slope is positive 1, right? But we just need a snapshot. Okay, make it just good. When you do it with a ruler, it's much easier. This program makes it a little bit, wait a minute. Well, I'm supposed to graph 1 over 4. Let's do that again. So 1 over 4, for that one, we're going to rise 1 and run 4. Okay, so rise 1 and run 4. I started graphing this point for some reason. Anyway, rise 1, run 4. So you rise 1, run 1, 2, 3, 4. So it's going to be somewhere here. Let's go ahead and graph the point. So let's see, from that, so from this point right here, somewhere here, all the way through that point. So you place your ruler, and you basically draw the line. But you just need a snapshot. Okay. So there goes the slope of that tangent line. Shift it down a little bit. Okay, now let's go to the -1 column. For the -1 column, we have 3, 2, 1. So let's see, for 3, we're going to rise 3 and run 1. So rise 3 and run 1, I'm going out of the paper. So instead of going up 3 and over 1, I can go down 1, 2, 3, and go back 1. Okay, so our tangent line is going to look something like that. But all I need is just a snapshot, right? So make it short. Just preserve the steepness as best as you can, okay? All right. And then the next one is 2. So for 2, we're going to rise 2 and run 1. Okay, so rise 2, run 1. It's too far, so I can basically go down 2, 1, 2, and back up 1. So starting from here, 1, 2, back up 1. So the line that goes through those 2 points gives you the slope of the tangent line. So go down 1, 2, back up 1. So we have this line right here, but all I need is a snapshot. So the line that goes through these 2 points right here. Not as steep as the original one. Let's make it shorter, because all we need is just a snapshot. Okay? Try and preserve the slope as best as you can. And then the next one is 1. So for 1, you're going to rise 1, run 1. So the line, the tangent line, is going to go through these 2 points. Okay, so we just need a snapshot of the slope, the steepness of the tangent line. So let's try to preserve the slope as best as we can. And there you have it. Okay? This is slope of 3, 2, 1. You can see the slope decreasing, right? The steepness of the tangent line is decreasing. Same applies here to 3/4, 1/2, 1/4. So that's the trend here. As you keep getting closer, if you're approaching the the y-axis, you notice that the tangent lines are getting more and more steep. And actually here you have vertical tangent lines, but we're not graphing those because we were asked to exclude x equals 0 from our graphing coordinates, okay? Now let's jump here. All you just have to do is replicate these tangent lines over here. Just copy the steepness. Okay, I'm going to just do that right now. Okay, so I just did a cut and paste, but you know how to do this already. Okay, so there goes the slope of this goes your slope field. Okay, this question hasn't showed up in the past 3 AP exams. I don't know if this is going to show up now, but it's just good to know how to graph your slope fields. Alright, let's move on to the B part. For the B part, we have to find the equation of the tangent line to the graph of y equals fx at x equals 1. Okay, so to write down find the equation of the line, we can use the point slope form of the equation of the line that you learned in algebra. Y minus y1 equals mx minus x1. Okay, and if you get y by itself, you have y equals y1 plus m x minus x1. And the calculus variation of this function known as a linearization, remember the linearization of x is given by f of a plus f prime of a times x minus a. They all mean the same thing, okay? Bottom line, we need x1, y1, and m in order to find the equation of our tangent line, okay? So since it goes through x equals 1, we also have this condition here. You want to keep in mind of f of 1 is equal to 1. So since f of 1 is equal to 2, that implies that the point 1, 2 is on the graph, the graph of y. Alright, so keep that in mind. So now that we have a point on the graph, we now know that x1 is equal to the x coordinate of that point, and then y1 is equal to the y coordinate of that point. We have 2 items that we need to create the equation of our tangent line down, the x and the y coordinates. Next thing we need is m. Okay, m is basically the slope of the tangent line at that point, dy dx at 1, 2. So all we just do is evaluate the differential equation at 1, 2, okay? So we know that, let's put this up here. We know that dy dx is equal to y plus 1 over 2, over x squared. Y plus 1 over x squared. Let me make sure that this is right. Yeah, that's right. So all we're just doing is looking for the slope at 1, 2. We just plug in 1 for x and 2 for y. Okay, so that gives us y plus 1, 2 plus 1 over x squared, 1 squared, 2 plus 1 is 3 over 1, which is 3. So there goes the slope. Now we have all the ingredients we need to write down the equation of our tangent line. So we're going to have y is equal to y1, which is 2, plus m, which is 3, x minus x1. X1 is 1. If we simplify that, we're going to have y equals 2 plus 3x minus 3, which implies that y is equal to 3x minus 1. So there goes the equation of our tangent line. It can also be used to do the linearization as we'll be doing in part D. Okay, so that's that. Now let's move on to question letter. So for part C, we are to find d squared y dx squared. So what on earth does that mean? D squared y dx squared. D squared y dx squared is basically the second derivative of the original function. Okay, so C, we have to find, let's write it down here, find d squared y dx squared. Okay, this is simply d dx, the derivative of the derivative dy dx. Okay, so if you multiply to get d squared y dx squared. So we're just basically looking for the derivative of the derivative, the second derivative of y. Okay, so let's go ahead and write down the differential equation, which represents the first derivative, dy dx is equal to y plus 1 over x squared. Let me scroll up and make sure I got that right. Okay, good. So we're going to just differentiate this, okay? I'm going to be using the prime notation here just for symbolic convenience, and then at the end I'll revert back to the other notation that I have. So what we're looking for is the prime of this dy dx prime. Okay, so this entire expression prime. Now, how do you find the derivative of a rational expression? Well, you use the product rule, right? So I'm sorry, the quotient rule, since you have a quotient of two expressions. So if you have u over v prime, do you remember the quotient rule? U over v prime is going to be v u prime minus u v prime over v squared. Okay, so we have low d high minus high d low over low squared. In this expression right here, y plus 1 is our u, and x squared is our v. Okay, so let's apply the quotient rule to this expression. Now you have to remember that you're differentiating with respect to x, so whenever we are differentiating any variable that is not x, we have to append d of that variable dx. Think about it as implicit differentiation. We're differentiating this implicitly since this is not an explicit function. When you're differentiating x's, you do not need to append any dd component because the x dx is just 1. But if you're differentiating y, you have to use dy dx because you're applying the chain rule here. Okay, so let me show you what I'm talking about right after I set this up. So we're going to have v, which is x squared, v u prime is going to be y plus 1 prime as vu prime minus u y plus 1 v prime is x squared, the denominator prime, divided by v squared. So v is x squared, so if we erase x squared squared, it's simply going to be x to the 4th. Okay, so x to the 4th. Now let's go ahead and differentiate this. We're going to have x squared. Differentiating this implicitly, the derivative of y is just y times dy dx, which is y prime, plus the derivative of 1 is just 0, minus y plus 1. The derivative of x squared is 2x using the power rule. 2x, derivative of x is the x dx, so that drops off, and we just have it like that. Okay, so do not forget to add y prime when you're differentiating the y term, right? And then the denominator is simply still x to the 4th. So let's see, simplify that. We're going to distribute x squared to that term right there, which yields x squared y prime minus minus 2x times y plus 1, okay? So let's write this down, 2x times y plus 1. I don't want to distribute this because I might be able to do a factorization later on, so I don't want to set myself up to fail. So let's leave it like that for now and make our substitution and see what we can do with that factor, that quantity in parentheses. The denominator is still x to the fourth. Okay, now what is y prime? We're now going to substitute the value of y prime, dy dx equals y plus 1 over x squared into this equation to finish off the expression for our second derivative, okay? So let's plug that in. We're going to have x squared times y plus 1 over x squared. That's substituting y prime for y minus 2x times y plus 1, and that entire expression divided by x to the fourth. Okay, let's see if we can simplify that. If you look at this, inspect it closely, you notice that we can cancel these two terms out. And then we have y plus 1 minus 2x times y plus 1 over x to the fourth, okay? Now you see what I was saying earlier about y plus 1 being able to be factored out. It can be factored out here, which makes our answer look pretty. So we factor out y plus 1, and we're left with quantity 1 minus 2x in the parentheses, and that divided by x to the fourth, okay? So that is the equation for expression for the second derivative. So the square y dx squared is y plus 1 times 1 minus 2x divided by x to the fourth. All right? Okay, now let's shift our attention to the next portion. Part D. We're to use our tangent line from C to approximate f of 1.1. And the question is this, it goes further to ask, is this a bigger or less than the actual value of f of 1.1, considering the result in C? All right, so what we're simply going to do is we're going to have this equation of our tangent line act like the function, and then we're going to use it to approximate the value of the function at 1.1, okay? All right, so let's go ahead and do it. So I'm going to call the tangent line L of x, okay? So this is part D. Part D, we know that the tangent line equation was y equals 3x minus 1. Let's call it L of x, okay? The linearization of the function, let's call it L of x, 3x minus 1. So f of x can be approximated using the linearization of the function. This tangent line, when you're really close to a particular point, L of x can act like a substitute for this function. Okay? So f of 1.1 is basically going to be L of 1.1, which is what you get when you plug in 1.1 into our function. So it's going to be 3 times 1.1 minus 1. Okay, so you're going to have 3.3 minus 1, which is 2.3. All right, so f of 1.1 is approximately 2.3. So the other part says that, is this an overestimate or an underestimate? Is it bigger or less than the actual value? So we also have to consult part C. So what does the concavity tell us about an approximation? So let's note the connection right here. So let's put a side note. Note the following. Okay. So note if the original function, if f of x is concave up, then the linearization of x is going to be an underestimate. underestimate. Okay, well, how do we know? Let's make a sketch. Let's say you have a concave, an upward function with upward concavity. When you draw a tangent line at any point, what do you notice? The tangent line is underneath the curve. Okay, so if the function is concave up, the linearization or the estimation with the tangent line is always an underestimate. All right. How about if the function is concave down? What do you think is going to happen? If f of x is concave down, then the linearization is an overestimate. Is an overestimate. Overestimate. Okay, so we have the, let's draw an example. Let's see, we have a function that has downward facing concavity on an interval. What do you know about the tangent lines on that interval? Wherever you draw the tangent lines, you're going to be it's going to be above the curve, right? So when you make any estimation, it's going to be higher than the actual curve. All right, so you have an overestimate situation here. Okay, so what role does the second derivative tell you concerning concavity? And you also have to recall that if f double prime is greater than 0, if it's positive, then the function is concave up, right? And if f double prime is less than 0, then the function is concave down. So all we just need to find out now is the sign of the second derivative. What is f double prime at x equals 1? Okay, so we're looking at x equals 1 because that's relatively close. That's what we use to write down the equation of the tangent line. Remember, we found the equation of the tangent line at x equals 1, so that's what we're going to be looking at right now. Okay, so we're going to find dy dx at x equals 1. So f double prime of 1 is equal to what we found before, d squared y dx squared, evaluated at the point 1, 2. Okay, so let's make sure I have this right. Yes, I do. Okay, so what is d squared y dx squared? That's what we found over here. So we're just going to plug in 1 and 2 into this function, and that should help us determine what our result is going to be. All right, so all I care about actually is the sign, okay? So y plus 1 is 2 plus 1 times 1 minus 2 times 1 divided by 1 to the 4th. Okay, let's simplify this. This is going to yield 2 plus 1 is 3. 3 times 1 minus 2 is negative 1 over 1. I don't need to finish this off. I just need to determine the sign. Okay? So what does this tell us? Well, if we work it out, you can see it's negative 3. So f double prime of 1 is less than 0. So if f double prime of 1 is less than 0, that implies that f of x is what? Concave down. If f of x is concave down, then the linearization is going to be an overestimate. Okay? So let's go ahead and write that down. The approximation of f of 1.1, which is linearization of 1.1, is an overestimate. On the AP exam, you have to explain your reasoning. Okay, you can't just say it's an overestimate. It's an overestimate because second derivative of x is less than 0 at x equals 1. Okay, so since the second derivative is less than 0 at x equals 1, f of x is concave down, and the tangent line lies above the function. Okay, so that's the importance of the second derivative. It tells us the behavior, the orientation of the tangent line relative to the curve around a neighborhood, not at the point. Because we know at the point, the tangent line and the curve are indistinguishable. But if you go outside the point, this situation that we're writing down here holds, okay? All right, so let's go on to the last portion. All right, so in part E, we have to find the particular solution to the differential equation with an initial condition f of 1 equals 2. Now, on the AP exam, this question, this portion of the differential equation section normally carries the highest amount of points. Normally, 6 points is a standard procedure. So if you just know how to solve the differential equations, and you do this accurately, you'll get over 60% of the points for this section. Okay, so keep that in mind. Knowing how to find a particular solution is really important. Okay, so let's go ahead and do it. Dy dx is equal to y plus 1 over x squared. All the differential equation problems that I saw in the AP exam are solved by separation of variables, so that's the technique we're going to be using here. So what does separation of variables mean? This basically means that you have like variables on the same side of the equation, okay? So let's keep the y's on the left side and the x's on the right side. To accomplish that, I'll have to multiply both sides by dx. That will get rid of this dx on the left side. And then there's y plus 1 up here, so I'll also divide by y plus 1 and y plus 1. It's just like you're solving a typical algebraic equation for a specified variable, okay? Okay, so let's see. These two cancel out. We have 1 over y plus 1 dy equals 1 over x squared dx, okay? Now, let's go ahead and solve this differential equation. To solve it, we have to do the opposite of differentiating, which is integrate. We're going to integrate both sides. So what you have is an integration problem where you have two expressions you have to integrate. All right, so we have two problems to integrate. Now, to find the antiderivative of this, you can use a u substitution, but if you take a look at the denominator function, if you call this u, du is simply going to be dy. And then to integrate it is just going to be the natural logarithm of u, and then you plug this back in, and then you just have the natural logarithm of the denominator, okay? So the antiderivative of this expression is simply the natural logarithm of the absolute value of y plus 1 using u substitution. And then here, I can write this expression as x to the negative 2 dx. Writing it like this makes it easy for me to use the power rule for integrals, okay? So let's go ahead and find the antiderivative of that. The natural logarithm of the absolute value of y plus 1 is equal to x to the negative 2 plus 1 is negative 1 over negative 2 plus 1, which is negative 1. Now there's something you must not forget, which is that c, the constant, when you're solving indefinite integrals. If you forget the c, you're going to lose a lot of points, okay? Right after you forget this c, you just get zeros, 0, 0, zeros, okay? So do not forget this c. It's very, very important, okay? So there goes the antiderivative of both sides of my equation. Now what I'm going to do is I'm going to proceed to find c, okay? So to find out what c is, I'm going to use, since f of 1 is equal to 2, this implies that x is 1 and y is 2. I'm going to plug these two values into this equation, and that will help me find the value of c. Okay, so this is the rule of this initial condition. So I'm going to have the natural logarithm of the absolute value of 2 plus 1 equals, let's see, 1 to the negative 1 over negative 1 plus c. Okay, so we have the natural logarithm of 2 plus 1 is 3 equals negative 1 plus c. That implies that c is equal to the natural logarithm of 3 minus 1. Actually, I'm sorry, plus 1. You add 1 to both places, so that's what c is, okay? So we're going to put this back into the equation. All right, so what we're going to do is go ahead and put this c back into this equation that we had right here. Our goal is to isolate y, okay? So we're going to have the natural logarithm of the absolute value of y plus 1 is equal to, we can bring the x downstairs using the reciprocal property of exponents, negative 1 over x, plus the value of c, which is a natural logarithm of 3 plus 1, okay? Now, to get y plus 1, this absolute value quantity, the argument of the logarithmic function isolated, we're going to get rid of the ln using its inverse, which is the exponential function. So e to the little ln of y plus 1, absolute value of y plus 1 equals e to the little negative 1 over x, negative 1 over x plus ln of 3 plus 1. Okay, like that. And on the left side, e and ln cancel each other out, so we have the absolute value of y plus 1 is equal to e to the negative 1 over x plus ln 3 plus 1. Okay? Now, in order for this expression here to satisfy f of 1 equals 2, this absolute value quantity must be positive. Okay, this must be positive. If it were negative, then it will be an undefined expression. It will be an inaccurate expression. Okay, so in order to satisfy this equation, since f of 1 equals 2 must be defined, then we have the absolute value, this quantity right here has to be positive, or else we'll have a mismatch with the sign, is equal to y plus 1. So we can drop the absolute value bars. We're going to have y plus 1 equals, now this e component right here, I can use the inverse of the product property of exponents to break this down. Okay, so if you remember back in algebra, if you have a product of exponents with the same base, so a to the x times a to the y can be written as a to the x plus y. We can go in this direction. We can also go in the reverse. Okay, so now we have the sum of the exponents. We can write them as the product of exponents with the powers as the addends that you were summing together. Okay, what I'm going to do is I'm going to group negative 1 over x and 1 together, because e cannot neutralize them, but e to the ln 3 can be simplified. So I'm just going to separate that, okay? So what I'm going to do is I'm going to take the two that cannot be simplified, I'll cluster them together, e to the negative 1 over x plus 1, and then e to the ln of 3, I'll keep it by itself because that can be simplified a little bit further, all right? So what is e to the ln 3? These are inverse operations. E and ln cancel each other out. So you're going to have y plus 1 equals 3 e to the negative 1 over x plus 1. To finish this off, you just simply subtract 1 from both sides, because the particular solution has to be in the form y equals. So if you subtract 1 from both sides, you have y equals 3 e to the negative 1 over x plus 1 minus 1. And that's the particular solution of a differential equation with the initial condition f of 1 is equal to 2. All right, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to our channel for updates to other cool clips such as this. And also post a comment to let us know what you think about this presentation. More clips can be found on mathgotserved.com/calculus. Thanks again for watching, and have a wonderful day.